In this video, we'll consider the vector product of two vectors. Let me remind you that in the previous video, we have studied the scalar product of two vectors, giving us as a product of two vectors a scalar, a number. Now, in this case of the vector product, we'll take two vectors, multiply them, and we'll get a vector. Okay, so let me define what is the scalar product, and that is the vector product of two vectors of A and B. So as I said, it has to be a vector, is a vector which we'll denote by A cross B. This is why it's sometimes called as the cross product, such that the following things are satisfied. First, A cross B is perpendicular to both A and B. So it should be perpendicular to these two vectors. As for the next condition, we have the length of the cross product, the length of this vector product should be equal to, so now we are specifying the length of this vector to be the length of A times the length of B times the sine of the angle between them. Okay, so it's very similar to the formula that we had for the scalar product, but it is only the length of the vector product, and it is taking the sine of the angle between A and B. So what is this length? Well, let me just try to sketch this out. So we have two vectors. You have to imagine these vectors being in 3D space, because otherwise the first condition would exclude all vectors but 0. So we have these vectors in 3D space, and we have the angle between them to be theta. So what this quantity is, the length of our cross product, is the area of this parallelogram that A and B spans. So this area, let me just quickly make a note here, this area is equal to the length of A cross B. Okay, so if you remember your trigonometry, you can give it a simple proof. So the area is A cross B, and for the last condition, for the vector product of two vectors, we have to have an extra condition, because let's think about the first condition, which says that A cross B should be perpendicular to both A and B. Well, if A and B span a plane, then A cross B should be along the line that is perpendicular to that plane. So imagine having this line at right angles to the plane. So A cross B, the endpoint of A cross B, should be along this line somewhere. Now the second condition restricts our possibilities, because it should be along this line, but only according to this formula, only at a distance from the common initial point, that is this far away. Now then we have two options. We have either this vector pointing up in this figure for A cross B, or we could have this vector pointing the opposite way, but having the same length. Okay, so they are the opposites of each other. They are the negatives of each other. So which one of these two vectors, which both are perpendicular to A and B and have length according to that formula, which of these should be the vector product? My claim is that it's the green one, this one pointing up in this figure, because of the third condition. So this will be A cross B, and let me use this figure to illustrate this third condition. It will say that the three vectors A, B, and A cross B in that order should satisfy the right-hand rule. So take your right hand, and if you take your right hand and slowly try to go around this line, sort of grab this line that is perpendicular to the plane, you should be able to grab it so that you first touch A, then B, and your thumb will point in the direction of A cross B. So this is the right-hand rule. Again, grabbing the line that is perpendicular to the plane spanned by A and B. First, I'm touching A, then B, and get my thumb in the direction that is the direction of A cross B. So A, B, and A cross B satisfy the right-hand rule. Okay. Now think of what would happen if I would go the opposite way. If I would took my right hand and wanted to grab this line, but in a way that I first touch the vector B. Now I have to go in a sort of weird way, and I have to go behind the line to first touch the vector B, then the vector A, and my thumb would point downwards, the opposite direction. So, and that vector is the opposite of A cross B, but now I first had B, then A, so this vector is actually B cross A. And just from this figure already, you can see that they are the negatives of each other. So A cross B, we can already see that A cross B, or rather, let me say B cross A, is equal to minus A cross B. Okay. Now, this is the definition of the vector product. So it has to be a vector that is perpendicular to both of the vectors that we started from. It has to have a certain length, which is the area of the parallelogram that is stretched by the vectors that we started from. And finally, the vectors in the order that we have written them, A, B, and then the vector that we obtain as a vector product should satisfy the right-hand rule. Okay, so this is how you define the vector product. And of course, you might wonder, why is it a good notion? Well, again, just by the definition, we can already see that it's a good way to, if we can somehow calculate this vector with coordinates, it's a good way to obtain a new vector that is perpendicular to two given vectors. Okay, so that is always useful. The way we are going to do this is, again, just by using the basis vectors. So let's say that A is expressed as a₁ times I hat plus a₂ times j hat plus a₃ times k hat, and B is expressed as b₁ times I hat plus b₂ times j hat plus b₃ times k hat. So these are the coordinates of our vectors. a₁, a₂, and a₃ are the coordinates of vector A. b1, b2, and b3 are the coordinates of vector B. And now we would like to calculate the vector product A cross B. using these coordinates. Now, of course, we just have to again do this enormous calculation of taking these two vectors in this expanded form and take their vector products, expand these, expand this product, which we can do, and that is something one has to prove separately, that it's okay to expand the product. And when we do that, again, we'll get 9 terms, but in contrast to the scalar product, in which we had only 3 terms surviving, the rest were 0. Now we have now we have 6 terms surviving, and it's the 3 terms that are going to become 0. So for this, in order for us to calculate this expansion, we have to know the vector products between the basis vectors, and let's just quickly try to list these. So the cross product, the vector product of I with itself is the same thing as j with itself, which is the same thing as k with itself, which is going to be the 0 vector. Why? Because this vector product should have the length involve the sine of the vector of the angle between these vectors, between the vector with itself as a factor. So of course it's 0, the angle between a vector and itself, so that will give us the sine of 0, which is 0. So the only vector that has 0 length is the 0 vector. Okay, and it's true in general. I should make a note of this fact somewhere, that A cross A for any vector will give me the 0 vector. Okay, so these are the 3 terms which are going to actually vanish, and it's also useful to see how they behave when we multiply them. We take the vector product of I hat and j hat. Now, what is that going to give us? What that's going to give us is the following. It's a vector that is perpendicular to both I hat and j hat. It should have length 1 times the sine of 90 degrees, which is equal to 1, this product. These are unit vectors, and the angle between them is 90 degrees. So it should have unit length perpendicular to both of these vectors, and the 3 vectors I hat, j hat, and this vector product should satisfy the right-hand rule. If you take all of these conditions into consideration, you will find that this vector is the 3rd basis vector k hat. And similarly, j hat multiplied by k hat, their vector product is I hat, and finally k hat will give you the vector product with I hat to be j hat. If you use these rules, what you will see is that the general formula for the vector product of 2 vectors given by their coordinates is going to be the following. It's going to be the vector which has coordinates a₂b₃ minus a₃b₂. This is the first coordinate of our vector product. So this is what multiplies I hat. Then the next coordinate for our vector product is going to be a₃ times b₁ minus a₁ times b₃. And finally, we'll have a₁ times b₂ minus a₂ times b₁. So this is the 3rd coordinate of our vector product, and that is what multiplies the unit vector k hat. Okay, so I hope you see the connection, how if we expand this product, we'll get these vector products, which will in turn give us this formula. I encourage you to actually do the calculation, expand those products, and collect the terms having factors multiplying I hat, j hat, and k hat, and find that this is indeed the coordinate expression for the vector product. Now, what I would like you to do to finish the video is to give me a vector, a unit vector. So this is just an example. Find a unit vector, a unit vector, perpendicular to the following vectors. A should have the coordinates 1, 1, and 0, and B should have the coordinates 0, 1, and 1. Okay, so find this vector, this unit vector that is perpendicular to both of these vectors. Pause the video and use the box below to input your answer. Okay, so I hope you have been able to find this vector. But first of all, a good idea to look for a vector that is perpendicular to both of these vectors is just to calculate the vector product. Their vector product using this formula can be calculated, and its coordinates will be 1, -1, and 1. Okay, so this is the vector product of A and B, these vectors. So this vector is definitely perpendicular to both of these vectors, but the additional condition that we had for this vector that we are looking for is that it should have unit length, and this vector currently has a length of √3. So if you square the coordinates, add them up, and take square root, you will get √3. So what we have to do with this vector is we have to divide it by its length. If we do that, we'll get a unit vector. Okay, and it will be the vector that is divided by √3 and has coordinates 1 over √3, -1 over √3, and 1 over √3. Okay, I hope you got this right. It's either this vector or the negative of this vector, so the vector with opposite with coordinates that have opposite signs. Okay, I hope you enjoyed this video, and I'll see you in the next one.